In this video, we are going to talk about support vector machines. Let's start with a cartoon illustration. We have points, data points, let's say, of two classes, a red donut class, class A, and a 5-pointed star, class B. So you have points here represented in two-dimensional space, x1, x2, and your task is to find a boundary around these points so that you can separate class A from class B. So you have to come up with a closed surface around a set of points, and that will be your decision surface, right? So decision surface is a pictorial representation, let's say, of a classification function. Your first example based on, let's say, decision trees that we have seen last week could be that let's think of a rectangle defined in this way. So if your x1 is between a1 and a2 and x2 is between b1 and b2, that creates a nice rectangle. All points within that rectangle are going to be class A points. All points outside the rectangle are going to be class B points. You could define another decision surface, let's say a circle, where you are defining what the center should be, what the radius should be, and then you can again see that any points inside of that circle are going to be class A, outside are going to be class B. Or you could come up with a very random closed surface that again still defines your decision surface, right? So given all of these, or any of these decision surfaces, when you have a new data point that comes in, so for example, this point which is unlabeled, you can label it using this decision surface as a star or class B, right? And that would be the decision for any of the three different variations we saw. So a classification function is represented by decision surfaces, and the problem then becomes, well, how can you find a surface and what is a good surface? Let's take another example. Here again you have points in x1, x2 in two-dimensional space, but here we are showing pluses and minuses as the positive class and the negative class. All these points shown in red are from the training data. So now, based on these training data, you are supposed to identify a decision boundary that separates the positive from the negative. You could come up with a complicated polygon, a pentagon here, that brings all the positive points inside and leaves the negative points outside, right? Or you could learn a line. A line is very easy to define, and if you are okay with making allowing some mistakes in the training, for example, in this particular case, there is one mistake in the positive class. So one of the positive points is on the negative side of the line, right? And there are three mistakes on the negative class because 3 points are on the positive side of this line. So you could define this line where anything above this line, that's towards where x2 is written, would be positive. All points below the line, that is where x1 is written, that is negative. And then you know that in the training phase, we have made 4 mistakes. When you had a polygon that you had learned, you had not made any mistakes. But lines are easy to find, easy to define, and easy to evaluate. Also, lines are more generalizable. And this follows this Occam's razor, which we again saw last time. And that is really that simpler models are preferred. Models that are less complex there are less chances of it making mistakes when in the test set. So that means they are more generalizable. To illustrate that point, suppose you had test examples that also followed the similar distribution as what you had in the training set, then you will see that the line actually would have made less mistakes here. So line would have called another positive instance as wrong, as negative, and really that's it, right? All of the other positive points would have been correct. All the other negative points would have been correct. Whereas the polygon surface would have made a lot of mistakes, not only in the positive point on the that line made a mistake on, but all of these positive points that are outside of the polygon, but would be considered as negative by this polygon surface. So this is like an illustration that when you are seeing your data set is a sample of an underlying distribution, and without knowing that distribution, it's probably best to make as fewer assumptions as possible. So that means kind of building a simple model, a linear model, is preferred. Okay, so that would be a linear boundary, right? So what does that mean? We have a line now separating positive and negative points. In this case, the positive and negative points are in such a way that there is a line that would separate them. That is called a linearly separable model. Data points, linearly separable data. So you found a line that separates the positive points from the negative points. Again, above the line is the positive side, below the line is the negative side. In two-dimensional space, recall that line is kind of written down as, in this case, x2 is mx1 plus c, right? M is the slope, c is the intercept. If you rearrange it a little bit, you can see that the function is something like mx1 minus x2 plus c equal to 0. So that will be that line, right? The dotted blue line. In general, if you have multiple dimensions in n-dimensional space, you could write down this as a dot product of w times x. So a dot product between w and x plus b, where again b is this intercept, and this is a dot product between the weight vector w and the input dimensional space x. So in our example here of two-dimensional space, we would have said w is a vector with m and minus 1 as the two coordinates, right? X would be x1, x2, and then b and c here are interchangeably kind of used. Okay, so once this is the function. Your function is w dot x plus b, and w dot x plus b equal to 0 would be your line, the line that is kind of shown here. And then the hyperplane is basically now a linear classifier because it is a line in this higher dimensional space. Specifically, then if when you put in any other data point, any other point x, any other input point x, if the value becomes greater than 0, then it's called the positive class. So if f of x is greater than 0, it's the positive class. If it is less than 0, it's going to be a negative class. So for example, think of the origin point here, 0, 0. If you put in 0, 0 here, the value will be b. Assume b is a positive number, then this fx will be greater than 0, right? The fx value will be b. And so it's a positive number, so the label that you will assign to a point on origin would be a positive point. Okay, so then the task becomes to learn a linear boundary is the same as learning this weight vector w. So how do you find this weight vector? Again, we have the same data set. It's a linearly separable data set. And finding this linear boundary is finding this line, and there can be many methods to kind of create this line. And one of these methods would give you a dashed blue line like this, but it could be the dashed green line, which is also separating positive points from negative points, or this dotted red line, which also separates positive points from negative points. So all these 3 points have 0 training error. And then the question is, which one of this is better? So even if it's a line, and we know that probably lines are better than these funny little shapes you could create, there can be infinitely many lines if the data is linearly separable. So if classes are linearly separable, then there exists multiple lines, infinite number of lines that can separate these in, and you can learn any one of these. And different methods might give you different approaches. So then the question becomes, which of these lines is the best line? So how do you find this reasonable boundary? One idea is, instead of thinking of it as a line, think of it as a band, a thick line, right? A line like a ribbon that you are trying to fit between the positive and negative points. The wider that band is, the more separable these points are. Okay, so you are trying to push these points as far away as you can, and then the goal of this kind of learning is to find the band with the maximum thickness. This is called margin. The thickness is called the margin because you are basically creating a margin, a boundary between the positive points and negative points, or frankly between any points, because you're trying to kind of push in positive points on one side of the boundary and negative points on the other side. The midpoint of between this margin is called the classifier, and these points that define the margin are called support vectors. Why are they called support vectors? Because those are the points that are supporting this margin. If one of them is kind of moved, then the line can be moved significantly based on that. So the line is the band is really defined by the points that are on the edges of that band. The line in the middle of the margin would be your classifier, and that would be called a maximum margin classifier. And in fact, support vector machine is really a maximum margin classifier. So support vector machine is a classifier that tries to maximize the margin between positive and negative points. Okay, so support vector machine is a linear classifier that can find a hyperplane to separate these two classes of data, positive and negative class. So given these data points x1, y1, x2, y2, and so on, the classifier learns a linear function w, or this weight vector w, such that w dot x, if it is greater than 0, then it's a positive class. If it is less than 0, it is negative class. And it creates it using an optimization function that maximizes the margin, which means maximizes the width of the line. Okay, so now that we see that SVM is a linear classifier that can separate two classes, what if we had multiple classes? Suppose now we have, in addition to red donuts and 5 pointed stars, we have green triangles, right? So now you're going to learn a classifier learn a linear classifier that separates 3 kinds of points. Is there a line that you can learn? No, because a line divides the space into only 2 halves, right? So it cannot really get 3 areas from there. But support vector machines can be extended to multiple classes by doing some tricks. So one of them is called a one versus rest model, or sometimes called one versus all model. Here, you try to learn a line that separates one class from all the other classes. So an example is here. This line separates the triangle class above the line and the other 2 classes below the line, right? So the positive class is the triangle class, the negative class is anything that is not a triangle. This blue line separates the stars from those that are not stars. This red line separates the red donuts from points that are not red donuts, correct? So suddenly you have taken this space and using these 3 lines separated it out such that you have a red donut space, you have a blue star space, and you have a green triangle space. So in general, if you had n classes, this one versus rest classifier would learn n different lines. Another approach is to not consider one class and all the other classes as a negative side, but pairwise classifiers. So one class against another class. So in this case, you would draw, you would learn a line that separates a triangle from a donut, or a triangle from a star, or a star from a donut. Now here too, by learning these 3 lines or line segments, and you see where they cut each other, and that kind of defines this space into again 3 unique regions, which is going to be the green triangle side, the red donut side, and the blue star side, correct? For a one versus one classifier model, because you need to create binary classifiers between every two classes, if there are n classes, you will learn a combination of kind of NC2 classifiers. Okay, so the other option issue is with linear boundaries. So consider this set. It's just one feature, x, let's say, and you have positive points, but you have negative points on either side of those positive points. Now, there is no line that splits the positive points from the negative points. You have to come up with some sort of a funny curve, right? There is no one line that can split it without making any mistakes. But actually, if you don't think of these as points only in one dimension, but if you change it such that you are let's say this is the x and y axis, or you are transforming it from a x space to an x squared space. Okay, so the plus point that is nearest to the y-axis, let's say, doesn't get improved as much. It continues to be just a small value because for small numbers, x and x squared are not that far away. When you have the next negative point that gets x square of that point as its y-axis, the other next one gets further up, and the next one gets further up. So you are transforming it from an x space to a x comma x square space, and the same thing with the negative side of this of the equations. Again, you have all the positive points kind of transformed into some sort of a parabola, right? And parabola kind of is one that defines an x square space. Okay, now in this space, you have a line that actually splits the positive points from the negative points. So what you have seen is this line in the higher dimensional space, in the x square space, corresponds to something like this in the original space. So even though an SVM classifier learns only lines, it learns it on the feature space you're defining it. So if you transform the feature space to a more higher order space, a line can still be learned on that higher order, and so SVMs can learn a classifier and to separate the positive points from the negative points, or to separate the set data set that does not appear to be linearly separable. The way to do that is using kernel functions. So kernel functions allows the model to kind of allows the feature space to be transformed to a higher order features, and so that you can learn a line in that higher order space. But the key issue is you can do that without really blowing up the number of features, more specifically without really reducing the efficiency by which you can compute distances. So because it's a dot products could be done very quickly. You can do that dot product equally quickly using higher order features without really explicitly modeling those features. That is using kernel functions. There are a lot of kernel functions. Linear kernel is basically the same as a line. Polynomial kernel will be a polynomial of higher degree, like degree 2, degree 3, and so on. A radial basis function has a Gaussian interpretation, so that's a slightly different formulation. In any case, these functions are crucial because SVMs can now learn what appear to be nonlinear decision surfaces, but using the same mathematical formulation as it was earlier. So to summarize, support vector machines are robust linear classifiers, and they are especially kind of robust and work very well with high dimensional data. And it is based on a strong theoretical foundation, specifically a quadratic optimization function. And they're expressive, especially using the kernel functions that allow learning a linear model in a higher dimensional space. And they can be extended into more than two classes using one versus one or one versus all approaches. And classes can be weighted differently as well. So suppose in your application, Missing cases, that is type 2 error, is more critical than identifying something wrong. So false discovery rate, that's type 1 error. You can weight the weighting scheme for learning the line so that you're not making mistakes in one kind of class, even if it means that you make some more mistakes on the negative side, right, on the other class. Okay, some of the disadvantage of support vector machines, or some of the kind of limitations, let's say, is that it handles only numeric features. So unlike decision trees, where it was really more tuned towards categorical features, but then you can learn new kind of thresholds on numeric features if you want to. Here, in support vector machines, they are mostly tuned for numeric features. But again, you can convert categorical features into numeric features. So if it's a binary feature, you can give it a number of 0 and 1 and convert it to a number. If it is a categorical feature with more than 2 different values, you can create multiple 0, 1 features, multiple binary features, and so all of those can be converted into numeric features, right? You could also do some normalization, or you need to do some normalization, because if your features are in very different space, remember that actually it's learning a dot product, so numbers that are in millions would suddenly weigh too much more compared to numbers that are in ones or fractions, right? So typically it's common for features to be normalized, that they are all 0, 1, all values between 0 and 1, or unit variation and variance and things like that. So it's common for some data transformation to be done before features are actually used by the SVM model. The other kind of limitation of SVMs is that these hyperplanes could be hard to interpret. It is basically a linear combination of the features, but though that linear combination may not actually be easy to understand. You could have weights associated with the features if you want to kind of understand that a little bit more, but it is somewhat non-intuitive, especially compared to decision trees and so on.